Hello there, my name is Zaki. I'm with my friends Riedho, Gifar, and Nara, and we're from Putri, and we're gonna talk about the zeroth law and why we think it's a fundamental law of physics. Let's begin with why we consider the zeroth law to be a fundamental law of physics. It is because the zeroth law is the foundation of thermal equilibrium, and without it, temperatures could not be defined and measured consistently. If this law didn't exist, things like thermometers would not be defined as a universal quantity, and thermodynamics would lack a consistent logical foundation. Why is that important, you may ask? Well, it's because the zeroth law establishes that thermal equilibrium is transitive. This allows all the systems in an equilibrium to be at the same temperature.
Now, what is the zeroth law even about? Well, the zeroth law states that if there were two systems that are in thermal equilibrium with each other, and a third system is added, that means the third system will have the thermal equilibrium with both of the two systems. Let's explain it in more details. Let's say we have three systems A, B, and C. If system A is in equilibrium with system B, and system B is in equilibrium with system C, then we know that system C is also in equilibrium with system A. This relationship is the essence of the zeroth law. Okay, but what does it mean when the systems are in thermal equilibrium? Well, it's when the systems are in thermal contact and allowing the heat to transfer between the higher temperature to the lower temperature, but because in equilibrium they have the same temperature, there will be no need heat transfers between the system, and their macroscopic properties remain the same. This means that things like pressure, volume, density, and etc. remains constant in equilibrium. And one last thing, does the system that are in equilibrium require physical contact? The answer is no. While yes, many systems reach equilibrium through direct physical contact, it is not necessary as thermal equilibrium can occur through radiation.
We will now find out whether thermal equilibrium behaves like a mathematical relation. We can do this by determining if the zeroth law can answer these three questions. The first question, is every system in equilibrium with itself? Yes, because thermal equilibrium is reflexive, meaning that a system will always be in thermal equilibrium with itself, because its microscopic are uniform and will not change. For example, let's say we spill with one system A into two parts A1 and A2, there will be no heat flow net. Then, since both parts have the same temperature resulting with A equals to A. The second question is, if equilibrium with B, is B automatically in equilibrium with A? The answer is yes. Since thermal equilibrium is symmetric, if system A is in equilibrium with system B, it means there are no net heat flows between the two systems, meaning that both have the same amount of temperature. A equals to B, B equals to A. For the third and last questions, does the zeroth law assert only transitivity? And again, the answer is yes. Because the zeroth law specifically states that if system A in equilibrium with system B and B system in the equilibrium with system C, then that means system A is in equilibrium with system C. A equals to B, B equals to C, therefore A equals to C. This is exactly the transitive property of a relation. Therefore, the zeroth law behaves like a mathematical relation. However, the zeroth law itself only states the transitive property, while the reflexive and symmetric properties flows naturally from the definition of thermal equilibrium. And because of the zeroth law, we can group systems into equilibrium classes. When two systems are replaced in thermal contact, we will observe one of two results. The first is nothing changed. If that means there is no heat flow. So the system are in equilibrium itself it change. That means there's heat flows and the equilibrium it reaches. Therefore, we can group the system together. All systems do not change. They replace it together belong in same group and systems that are not in the same group. The mutual thermal equilibrium. For example, if system A in equilibrium with B and system A is equilibrium with C, then A, B, and C belong in the same group. We can also have temperature as a numerical level. When the group are formed, they can assign a number to each group as seen as in this table. For example, their system equilibrium class temperature. A class 1, the temperature is 300 Kelvin. B class 1, the temperature also 300 Kelvin. C class 1, the temperature also 300 Kelvin. And D class 2, the temperature is 350 Kelvin. Systems in the same group have the same temperature while systems in a different group have the different temperature. Here temperature acts as a label that is used to identify which equilibrium group it belongs to. From this we may ask, why does transitivity allow the sign number T to describe equilibrium? Let's reminder back to the transitive property of the zero law states that if A is equilibrium with B and B is equilibrium with C, then A is equilibrium with C. This is important as ensure consistency. Example, for A and B both match a thermometer C, then they must match each other, and therefore one single value T can represent an equilibrium state.
Zhoqqi experiment suppose the zero law failed. Now let's do a Zhoqqi experiment. Imagine a universe where thermal equilibrium is not transitive. A is in equilibrium with B, B is in equilibrium with C, but A not is in equilibrium with C. This directly violates the zeroth law of thermodynamics, which normally guarantees that equilibrium relationships are consistent. From this, we can ask a few questions, like cold thermometer axis, we construct a temperature scale, or will the words hot and cold still be meaningful? Let's answer them one by one. The first one is simple. Thermometers would not exist because a thermometer works by raising an equilibrium with a system correspond to the same temperature for all systems in that equilibrium state. Example, thermometer B could be in equilibrium with A. The same thermometer B could also be in equilibrium with C, but A and C is not in equilibrium. That means that the thermometer is giving the same reading for two systems that are not in equilibrium, and therefore the thermometer would not provide relevant information. For the second question, we will not be able to construct a consistent temperature scale, as temperature scale works by assigning a single number to each equilibrium group of each system. Let's use an example. In our universe, if A equals B and B equals C, then A equals C. So all three belong to one class and get one temperature value. In the hypothetical universe, A and B must share the same temperature. B and C must share the same temperature, but A and C must have different temperature. Mathematically, this creates a contradiction where TA is equal to TB, TB is equal to TC, but TA is not equal to TC. A single numerical scale cannot satisfy this condition, so temperature could not be defined consistently. And for the last questions, the word hot and cold will lose their meaning normally. If A is hotter than B and B is hotter than C, then A must be hotter than C. Without transitivity, this ordering could break down, thus resulting with these possible situations. A feels the same as B, B feels the same as C. but A and C exchange heads. So the concept of ordering systems by hotness becomes inconsistent. People cause to describe local heat flow. Heat moves from one object to another, but they call it not like saying universal ranking of hotness. Thus, hot and cold will only be context dependent. They will not form a consistent global scale.
From all of that, we concluded that the zero law is not merely common sense or definition. As the law states, that thermal equilibrium between systems behaves as a consistent relationship. This means that thermal equilibrium is not just an experimental observation, but it is a universal relation that applies to all thermodynamic systems. The zero law also guarantees that equilibrium is transitive, and because of that, the systems that are in mutual equilibrium can be grouped together and assign the same value of temperature. This allows temperature to function as a single physical variable that describes the thermal state of a system, and without it, temperature could not be defined consistently across different systems. Thermometer owes their existence to the zeroth law. Because of the zeroth law, we know that if the thermometer is in equilibrium with the system, both must have the same temperature. This allows the thermometer reading to represent temperature of a system being measured. Lastly, the zeroth law provides the logical foundation for thermodynamics measurement. As all temperature measurements in thermodynamics rely on the assumption that equilibrium relationships are consistent and universal, the zeroth law ensures this consistency. Without it, thermodynamics measurement would become unreliable because equilibrium relations could contradict each other. Although historically formulated after other thermodynamic law, it is logically the most basic law of thermodynamics. It provides the essential framework that allows temperature to exist as a well-defined and measurable physical quantity. That's all. Thank you. Bye-bye.